Good evening, everyone. Welcome back to another Keep Looking Up. I'm Tiffany Woolbrick, and with me is most of the rest of the Ward Beecher crew. I have our planetarium engineer here, Kurt Spivey.
Evening, everybody.
And our students, Eleni Hensick.
Hello.
And Nishan Adhikari.
Hello.
We have a great show planned for you guys again tonight. We're going to be talking about stars and how we organize them, how we understand them, and how they are born and how they die. It's going to be great. If you're tuning in now, let us know where you're coming in from. We'd love to hear all the different places that you guys are joining us from. And we will start first with a sorry about that. That's my son. He needed to go for the potty. We will. So we're going to start with a star talk, a little look at the current nighttime sky, and we're going to do that with our senior, Eleni. And she'll be leading our Star Talk this evening. And I do want to mention that this is going to be Eleni's last show. She's graduating soon.
I'm sad. I'm going to miss doing these.
So give her your well wishes in the comments below. We are so proud of you, Eleni. Eleni is going off to graduate school in Arkansas, right?
Yes, the University of Arkansas.
So congratulations, and we wish you the best of luck on your new adventure, and we sure will miss you here at Ward Beecher.
I'll miss you too.
All right, well, would you like to kick us off with this?
Yeah. So I will share my screen. And hopefully you all can see this. So here I am using a software called Stellarium, the same software we use for all of our Star Talks. It's free. You can download it on your laptop or your phone, and it gives you a look at the night sky. You can look from any location on Earth, and you can set the time to whenever you want. But today I am set to Youngstown, where Ward Beecher Planetarium is located, but this is a live stream, so you might be watching from anywhere in the world. And depending on where you go, the sky does look a little different. If you travel very far north or very far south, you will see a slightly different sky, but a lot of these things you can see in most of the northern hemisphere. And the time right now is set to roughly now, a little bit after 8 o'clock. And sunset today is at 8:20, so you can see the sun is over by the western horizon, about to set. And we will just move forward in time here using Stellarium until after sunset. We'll go to about 9:30. And so this is what the sky will look like from Youngstown at about 9:30 tonight. I mean, it's cloudy, so not really. If there were no clouds, this is what it would look like. But the things I'm going to show you tonight are things that you'll be able to see over the next few weeks and months as we move into summertime. So if you can get out on a night when it's not so cloudy, try and look for some of these things. But before I get started, today is May Day, which is actually astronomically significant, which I didn't know until recently. So May Day is halfway between the spring equinox and the summer solstice. So just as a refresher, I know we've talked about this before, but if you're tuning in for the first time, so the equinoxes are, there's the spring equinox and the fall equinox. Those are the days of the year when we have equal amounts of daylight and darkness, and then the summer solstice is when we have the most hours of daylight out of any day in the whole year, and the winter solstice is when we have the least amount of daylight over any day of the whole year. And May Day, like I said, is halfway between the two, and we have 4 of these cross quarter days. The other ones are Halloween, October 31st, Groundhog Day, February 2nd, and August 1st. And again, those are just some of the names of those days, but different cultures have different names for those days, because while cultures may be very different from one another, we all do share the same sky. So most cultures do notice these things. But that's what's going on today. And another thing that I did want to mention, because people always ask me about this, people always ask me if there are any meteor showers coming up or any meteor showers going on whenever I do these talks. And in the next few days, we have a pretty small one. It's not anything too crazy, but it's called the Eta Aquarids, and those are meteors that are caused by debris from the famous Halley's Comet. And it usually peaks in early May. And the meteors, if you see any, will be pretty faint. At the peak, it will be about 40 meteors per hour. But we do have a waning moon phase right now, so the moon doesn't rise until really late. So the sky should be pretty dark. We won't have any light from the moon getting in the way of that. So if you do have time to get out to a dark place on a night that's not cloudy, you may see some faint meteors. So we are facing north right now. And the first thing that I want to bring your attention to is actually in the west. So here we do have these cardinal directions to help us, but in real life, we know the sun sets in the west, so just face in the direction that the sunset was, and you will see this object here. This is the planet Mars. It's the only planet that is visible to us right now. And one way to find it, where it is right now, of course, planets appear in different parts of the sky over time, but currently and over the next few days, Mars will be roughly in this area. If you look for this bright curve of stars here, if you've seen our shows before, you will know this is the top half of the winter circle. So Mars is kind of right in the winter circle just after sunset. And be careful not to confuse it with this star here. This is Betelgeuse. It's a red giant star in the constellation Orion. And a red giant is just a really big red star, and you can see the reddish color, just like Mars, but they're red for two completely different reasons. You'll learn more about why red giants are red in Kurt and Tiffany's talks about stars after this. But Mars is red because it has iron oxide or rust on its surface, and it reflects sunlight, and we can actually see that reddish color all the way from Earth. So Mars is pretty cool to see in the sky, I think, because you can see the color of the soil on Mars from Earth. But that's the only planet that's visible tonight. So next we will talk about the stars. So we'll face back to the north. And again, in real life, you don't have these big red letters to help you, but don't worry, here in the Northern Hemisphere, it is very easy to find north. You just have to look for a famous pattern of stars in the sky called the Big Dipper. And that is right here, I'm tracing it. But the Big Dipper is part of a constellation called Ursa Major. So I will show you the outline for Ursa Major, or the Big Bear. And it is upside down right now. Around this time of year, it will be high in the northern sky. But these stars are what we call circumpolar stars. And that just means that they move around, polar, the pole of the Earth. So throughout the year, this constellation, Ursa Major, will move in a circle around where the North Pole is pointing, which happens to be this star here called Polaris. And you can find Polaris by finding the front cup stars of the Big Dipper and tracing from the bottom through to the top. And Polaris is in a constellation called Ursa Minor. And you notice this is also the Little Dipper. So that is how you can find north. And by the way, the Little Dipper is very, very faint. Usually I can only make out these two front stars of the cup and Polaris, also known as the North Star, by the way, because it points you directly north. But if you can see all of these stars, that's how you know you are in a really dark place, a place that's very good for looking up at the sky. But don't be discouraged if you can't see those stars, because there is still a lot of cool stuff you can see in the sky. So this method here that I showed you for finding Polaris is called star hopping, and we're going to be using that to find some of our springtime constellations. So as I said, these stars here are circumpolar, but as you get farther and farther out from Polaris, which the pole points at, then stars will rise in the east and set in the west as the Earth rotates. And because of this, throughout the year, as the Earth moves around the sun, you will see different stars depending on which season it is. So the Big Dipper can help us find some of those springtime constellations. Now we're going to focus on the handle of the Big Dipper. And you notice it's kind of shaped like an arc. Well, you can trace that arc and keep going. Again, we're going to do a star hop and arc to this bright star here called Arcturus. And Arcturus is the brightest star in the constellation Pleiades, the herdsman. And I don't know how to draw a herdsman, but most of us here see it as an ice cream cone, where these three bright stars make a triangle of the cone, and here is a scoop of ice cream. And there's kind of a bonus constellation included here. This curve of stars right here is called Corona Borealis, but I see it as a second scoop of ice cream that fell off. Corona Borealis means northern crown, which this actually does kind of look like a crown. So if you see it that way, that works too. But going back to our star hop, so we arced to Arcturus from the Big Dipper, but we can also spike down to Spica, this star here. And this is the brightest star in the constellation Virgo, which I see as the letter V for Virgo. So these curves of stars here look like the letter V. But here's the outline as well. These stars over here are a little bit fainter, so it's a bit harder to see. But these are all springtime constellations. They are best viewed in the spring. And as you can see, they are rising here in the east. But I want to see some summertime constellations, because I'm really looking forward to going out at night when it's warm in the summer. I don't have to be freezing. As much as I love to look at the wintertime sky because it's beautiful, it is so cold. And summertime is great for stargazing, just going out and laying in the grass and looking up at the sky. So to see the summertime constellations right now, we have to stay up very late. So I am going to move forward in time. Here, let's face north again, because I told you about those circumpolar stars. Watch this. So here's Polaris. Earth's axis that it spins on is pointed at this star, Polaris, and you can see everything else moves around it. So we're going to stop. It's about 1 a.m. now. So you have to stay up pretty late right now to see our summertime constellations, but in the next few weeks and over the next few months especially, these will be higher and higher in the sky, earlier and earlier. So in order to see those, we are going to turn to the east. And you'll notice this bright pattern of stars here called the summer triangle. So this is not an official constellation. It's what we call an asterism. Astronomers have 88 official cataloged constellations, and this covers the whole sky. This is how astronomers map and catalog objects in the sky based on the official constellation that they're in. But for those of us who like to look up and look at the stars, it's easy for us to use these patterns or asterisms to help us find other things. So here is the summer triangle, because it's shaped like a triangle and it's best seen in the summer. Very creative. And these three stars are the three brightest stars in their respective constellations. So the first one is this star here. This is Vega, and it's the brightest star in the constellation Lyra, the harp. Again, a lot of these constellations don't really look like what they're supposed to, or they're things that are really hard to draw. So I'm going to zoom in on this because it makes it a little bit easier to see. I can't draw a harp with these stars. I usually just see this parallelogram shape and then this little triangle that includes Vega. And then the next star in this in the summer triangle is Deneb, which is the brightest star in Cygnus the Swan. Cygnus is actually pretty easy to draw and looks like what it's supposed to, a swan. So Deneb is the tail of the swan, and the body moves forward like this to the middle of the triangle, and the wings extend out like this on either side. And this is a really cool constellation because if you are in a dark enough sky, the swan actually appears to be flying along the Milky Way. So if you're looking for the Milky Way in the night sky and you want to see it, this is a good place to look. The Milky Way kind of just looks like a fuzzy, very faint cloud of light just with your eyes, but it is still really cool to see and think about how you are looking at light from tens of thousands or hundreds of thousands of stars. And the last constellation in the summer triangle is connected to this star here. This is Altair, the brightest star in Aquila the Eagle. And Altair is sometimes seen as the eye of the eagle, and here's the head, and the body comes back like this. And the way I see it, there are a lot of different ways to draw this one. The way I see it is this bright curve of stars makes the tail feathers of the eagle. This is really prominent, I think, at least in the real night sky. So I always find this to sort of mark the end of the eagle, and then trace the wings up like this. So its wings are outstretched, kind of like the eagle on the back of a quarter. And that is how you draw Aquila. But another cool thing about the summer triangle that I really like is that it also comes with bonus constellations, just like Boötes from the springtime sky. So the first one is this one here. This is Sagitta the arrow, like an archery arrow. So here's the front of the arrow, and this would be like the fletching back here. And then right below the triangle is Delphinus the dolphin, which is also cool because I think it actually looks like a dolphin. So this would be the nose of the dolphin. And then there's a little fin back here, and here's the tail. So if you get a clear night in the summertime, definitely look for these constellations, or at least the summer triangle, which you can actually see even if you don't have a super dark sky. So I didn't really talk about this very much, but I'm sure you've heard about it. There's this thing called light pollution that's caused by cars and streetlights and city lights and any lights that are turned on outside at night, and they make it really hard to see some of these stars. But the summer triangle is something that you can see from almost anywhere as long as you have a clear night. And if you want to see these fainter stars, then go out into the country or out somewhere where you know there aren't a lot of cities nearby that will be shining lights that make it hard to see. And it also helps when the moon's not up. So now and the next few days will be a very good time to look up at the sky because the moon is waning, which means the moon phase is getting smaller and smaller and closer to a new moon. So the moon won't be getting in your way when you try to look at the stars. But that is all I have for you. So next I'm going to hand it over to Kurt to tell you about stellar life cycles.
Thank you, Eleni. And as you saw mentioned in our little description of the show, this cross-quarter day of May Day in English was known to the Celts as Beltane, which was one of their big holidays. And it's the opposite of Samhain, which is Halloween, the cross-quarter day for autumn, which we talk an awful lot about in our show, Night Lights, which we definitely hope will be coming back this year when we get back to doing live shows in the planetarium. So yes, we are going to talk about life cycles. Eleni mentioned the different colors of the stars. To us, they look like points of light, but stars are all different sizes and colors, and we know an awful lot about them for just being points of light in the sky. And I just have to share and present so you can see what we know. We know all of this about how stars form, how they live, how they die. And it all depends on the size of the star that we're talking about. This is just a little overview. I'm going to get to a lot of this stuff. The first thing we need to know about is where they form. They form in things we call nebula. The plural of that is nebulae. So that's Latin. Matter of fact, it is the Latin word for cloud. These were clouds in the nighttime sky. The nearest star forming region to the Earth is the Great Orion Nebula, which is setting with the sun right now in the western sky. So we'll see it again in November. This is not the Orion Nebula. This is another nebula. But basically what this is are clouds of gas and dust, mainly hydrogen, but they could have lots of other elements in there that come from something I'll talk about in just a minute. But the gas is not even throughout the cloud. It's lumped up. And when it gets lumped up, that creates gravity. And when it creates gravity, it starts pulling more stuff in. And when more stuff gets lumped in, then the gravity gets stronger and stronger and stronger. As a matter of fact, it gets so strong that the hydrogen molecules can't stay apart. The gravity actually slams them together and they make a helium molecule. That is known as a nuclear fusion reaction. And when there's enough gravity to cause that, that creates a nuclear reaction that then sends radiation pressure out. And that is when a star starts glowing. When its nuclear furnace lights off, it begins to shine. The reason we can see these nebulae is because there are stars in there, like all these guys in here, that have already lit off, and their glow is exciting the gas around it, causing the gas to glow. And it's also reflecting off the dust, which is this area over in this part right in here. So when stars are born, they're very, very hot. And the color of a star tells you its temperature. When stars are, they're really easy to remember these different star temperature colors. This is the Pleiades in the constellation Taurus. These are very young stars. They're only a couple of million years old, so they're very hot. This is like the blue flame on the gas of your natural gas hot water tank, or on if you have a gas stove. The flame's very, very hot. It's blue. You also get yellow stars. Look at a candle flame. That's kind of a medium temperature. That's what our sun is. Our sun is a medium temperature star. And then if you have a campfire going, you put out the campfire and the embers glow. What color do they glow? They glow reddish orange. Those are the very coolest stars. So you can actually tell the temperature by looking up in the nighttime sky and seeing what temperature they are. I had brought up this particular picture of the Pleiades, number one, because my cat is named after this one right here, Merope. But number two, this is a time lapse, and you can actually see what's left of the nebula around these stars. They have blown away most of it with their nuclear fusion reactions, which creates solar wind, and it blows most of this stuff out. Some of this dust hangs around, though, and makes planets in these systems, too. We know that now. But they're all very hot. But I wanted you to see in a time-lapse photography, you can't see this just with your eye, but you can when you're taking long exposure photographs of the area of the sky. So after a while, stars settle down into what we call the main sequence. And what a main sequence star, like our sun, is doing is in its core, it's taking hydrogen and it slams the hydrogen together and makes helium. And it will do that for as long as it has hydrogen inside to do that. We can actually look at our star and we can measure how much hydrogen it has and how much helium it has. And we know from quantum mechanics, Einstein and Niels Bohr and Edwin Schrodinger and all those guys, we know how long it takes to make hydrogen, make that much helium out of hydrogen. So we can actually estimate our sun's age and how much longer it will go by the amount of hydrogen to helium that the star has inside of it. And we can actually measure this on other stars too. Tiffany will be getting into that a little bit later. But any star in this phase, what we call the main sequence, where it spends 75% of its life, it's going to be taking those hydrogen, slamming and making helium. That creates radiation pressure pushing out. And then gravity, because it's got so much mass, is trying to pull in. The reason a star is a ball is that's the most compact shape it can be. And a star is a constant battle between gravity trying to pull in and radiation pressure pulling out, which holds the size of the star. Now, one thing we don't know very well is what causes stars to be different sizes to begin with. Some stars are only a little bit bigger than the planet Jupiter. We call those red dwarf stars or M stars. And there are lots and lots of those out there. Matter of fact, if I think Jupiter was 2.5 times bigger than it currently is, it could have been an M star too. It's made of the same stuff as the sun. Medium stars like our sun are what we call G stars. They're not too big, not too little, medium temperature. And then the very big stars are what we call O and B stars. And these are big, super giant stars that are way bigger than our sun. How long a star lasts, you can kind of think of this as a car that was built at Lordstown. And when it came off the assembly line, they sealed the gas tank so you can't put any more gas in it. Those big stars are like Cadillac Escalades. They're big, they're powerful, they can really move, but they run out of gas pretty fast. Those stars don't last very long. Our sun, it's a medium-sized car. It's say like, you know, a Buick Encore or a Chevy Trax. It gets decent gas mileage, but not the best gas mileage. Our sun has been around for about 5 billion years. It'll be around for about another 5 billion before it runs out of fuel. And then the very smallest stars, those are the Toyota Priuses of the star world. They go along. As a matter of fact, we know of some red dwarf stars, M stars, that are on the age of our galaxy. They've just been burning along and they got a long time to go before they run out of fuel. So that's how stars spend most of their life. And everything you see there happens the same for all stars, no matter what size. They're all born in nebulae. They all start off hot and then they settle down in the main sequence. What happens next, though, depends on the size of the star. M stars, when they die, they don't do much. They just puff off their outer layers. They shrink down to about the size of Jupiter. They glow white hot for a little while, what we call a white dwarf. It's kind of like the dying ember of a campfire. And then eventually they go out and they become what we call a brown dwarf, or they're just a little remnant that's left around. So now what's going to happen to our sun is a little more pretty. It's not all that much more spectacular than what happens to an M star. Our sun is going to gently blow off its outer layers into space, shrink down about the size of Jupiter, and eventually stop glowing. But when it blows off its outer layers in space, it makes something like this. These are what are known as planetary nebulae, named by William Herschel, the guy who discovered Uranus. He was so excited about finding Uranus, he saw these things around other stars and thought they must be planets forming, so he called them planetary nebulae, but they have nothing to do with planets whatsoever. But they come in all shapes and colors. These are all pictures from the Hubble Space Telescope, but the star is down there in the center, is blowing off its outer layers. They form in different ways. The reason you're seeing interactions like the Butterfly Nebula up here is because there's another star that's still orbiting the one that's blowing off its layers, and the gravity from that star is keeping the gas from going out this direction and that direction, so it just shoots out these ends here. Same with this one down here. This is a pretty dirty one here. There's multiple interactions. So you got lobes of gas going off in different directions all over the place. But that's what our sun's going to do. But when you get to those big stars, the O stars, the M stars, these are big stars. And like I said, they're very powerful. And this picture, this beautiful picture, is brand new. The Hubble Space Telescope turned 31 on April 25th, and this was its 31st birthday picture. What you're looking at here is a supergiant star that is about to die. This is a very, very hot blue star. I think it's a B star, if I am not mistaken. And what happens in these big stars is they're so hot down in there. When they run out of hydrogen in the core, they don't like that. They want to keep glowing. So they start taking the helium that they've made, and they start slamming the helium together and making a heavier element. And they keep doing this. What's happening in this picture here is helium is now being formed in the center, and it's blown off its outer layers. Now, it'll keep taking these things, and they'll slam together. They'll make carbon. They'll make oxygen. They'll make all these big elements until they get to iron. And when a star gets to iron, you can't slam iron together and make everything else. And all of a sudden, the nuclear fusion shuts off when it gets to iron. We call that the iron catastrophe. Now, when that happens, gravity, which I remember I said it's radiation pressure pushing out, gravity pulling in. When the radiation pressure stops, gravity says, I win, and everything falls into the center of the star, but then it rebounds in a huge explosion called a supernova. Now, this is not a supernova in progress. It's just blown off its outer layers. It's still got some time before this goes supernova, but it's not too far away. Now, we haven't seen too many supernovae recently. The most recent one we know of happened in a satellite galaxy of the Milky Way called the Large Magellanic Cloud. It's called supernova 1987A. So one of the very first things the Hubble Space Telescope took a picture of, as a matter of fact. What you're looking at here is what we refer to as the Crab Nebula in the constellation Taurus the Bull. And this is what's left over after a supergiant star has exploded. And we know exactly when this happened, thanks to Chinese astronomers. In the year 1054, the star that created this Crab Nebula got bright enough to see during the daytime for several months. It was bright enough you could see it during the day, and then it abruptly disappeared. And then when the age of telescopes happened, we pointed up there and found the Crab Nebulae. So what's left of the star is down there at the center, and this is all what's rest of the star expanding out into space away from the center. Now, what happens in the center there depends on how big the star is. You might have a neutron star down there, which is an incredibly dense group of stars that atoms that have been stripped apart, and all that's left are the neutrons in the middle. And those are maybe about the size of Earth, but still weigh what the star used to weigh. They're huge. But something else can happen too. If it's big enough, there's so much gravity in there, not even light can escape, and it will become a black hole. Which we talked about last Monday in our Cosmic Conversations. I encourage you to go check that out on Facebook and learn more about black holes too. But if you've ever been just outside my office in the back hallway of the planetarium, this will look very familiar to you. This was actually done by the Chandra X-ray Observatory. This is kind of a summary of what I just went over here. So you have protostars forming out of the nebula. And then depending on their size, they will become main sequence stars. O and B stars are up here. Our sun is a G star. Here's an M star. Brown dwarfs are not stars. They are not having nuclear fusion going on inside there. They never got hot enough for the hydrogen to slam together to make helium. And we've discovered a lot of these around there too. So red dwarfs live a really long time. They blow off their outer layers, and then they become a white dwarf. Our sun becomes a planetary nebula and then becomes a white dwarf. Bigger stars also become red giants. They can also shrink to a blue giant, go off in a type 2 supernova, and then can be a neutron star or a black hole. And then what's left, the supershell, once again becomes a stellar nursery and starts making protostars. So it all comes around in a circle. But why are these called O stars? Why is our sun a G star? Why are these M stars? Well, I am going to turn you over to our planetarium lecturer, Tiffany, who is going to tell you where all that stuff came from.
Thank you, Kurt. I always love to hear about a star's life cycle. I think it's really interesting. And I'll share my screen here so we can get behind this story of, as Kurt mentioned, why are we calling things O stars and M stars? Why is our sun called a G star? There is a lot of significance around this, both behind this, there's scientific significance with these letters, but also historical significance. And it's a really great story. So I'm looking forward to sharing that with you. Before I get started, if you have any questions about anything that's come up with Eleni or Kurt or with my talk, or if there's just anything that you want to learn more about, please drop those questions or comments in our comment section, and we'll be happy to get to those. We love to hear from you guys. So anything you want to know about or any questions you have, let us know, please.
Yes, that's like a whole semester of college I just went through in about 15 minutes. So please ask questions.
Yeah, and if you felt overwhelmed with both Kurt's talk and my talk, this is very, very dense. So there's not a test after, no worries. So this is a stellar classification chart that I do like a lot. The only thing I don't like about it are that all these numbers here that are probably distracting you. This way, these are numbers or temperatures. This has to do, I believe, with the mass. Honestly, it doesn't matter too much. What I want you to notice here are first the letters. And you might notice that they don't really make a lot of sense. They're not in alphabetical order. They're not in any sort of sequence. And there's a great story behind why that is the case. But these O stars in general, this is represented by temperature. So these big blue stars that Kurt was talking about, we call those O stars. And then those smaller, cooler red stars are M-class stars, and we have all of them in between. We also do a subcategory of each of these letters using 0 through 9 to, I guess, be more specific about a star. So as an example, our sun is a G2 star. That means that it is a yellow star that is 2/10 of the way towards an orange star. So it's a G star that's moving towards the K just a little bit, 2 out of 10. So 2/10. Okay, if that makes sense. If it doesn't, that's okay. This is something called an HR diagram. This is how astronomers view the stars. So we often, many of us here, we love to go outside and look up and enjoy the stars, look at constellations. And when we think of an astronomer, we think of an astronomer outside looking up through a telescope, which they do love to do. But in practice, a lot of them stare at charts like this. So a lot of them see stars on a diagram like this. We have temperature measured here on the bottom, and this really gives you a good like intuitive idea of where those letters land in terms of the temperature of a star, the luminosity or the brightness of the star. And included on this is the mass of the stars. We compare them to our sun. So for example, these bigger stars up here would be 30 times the mass of the sun. Pretty straightforward there. You can see that our sun lays right here on this. This line is called the main sequence. Kurt mentioned that in his talk. This is where most stars lie on this diagram. So most stars fit really nice and neat on this little line here. But why do we do how do we know where stars lie on this line? And what does this tell us? What is the significance of this? This is an area of astronomy, discovering this HR diagram and learning about stars and their light. It's an area of astronomy called spectroscopy, which I find fascinating. And it has to do with light. We know so much about stars in our sky by studying their light, the light that they're emitting and shining on us. So when you go outside, and today, I hope you guys got to go outside today, at least here in Youngstown, it was sunny and beautiful, little chilly, but very sunny. And that sunlight that you feel in your skin during the day, it looks white to us, but it's not. It has many colors in it, and actually it's holding a lot of information. Sunlight holds information. It can tell us our sun's age, our sun's composition, what elements are in our sun. Many different aspects of a star can be learned just by looking at its light. But you can't just look at the white light. You have to break that white light into its component colors, like you do with a prism. If you've ever played with a prism, white light comes in, it's refracted and scattered around so that you can see the rainbow of light. This is actually what white light looks like. It's just that our eyes put it all together and create that white light. And this is a representation of the visible spectrum. So we can see, this is actually all of light. Okay, so there is a whole lot of light waves that we cannot see on this side of the visible spectrum. Whole lot of light waves we can't see on the right side, but that teeny tiny little band, that is all of the light that we can see with our eyes. And you can see on the purple side those are more energetic waves, light waves, and then on the red side they're less energetic light waves. So that's how you can kind of break them up into different components. And this is something that's been understood for a really long time, like back in the Newton era. Now, how does that help you learn about stars? It turns out that when you break up a star's light into its different colors, it does not just shine a continuous rainbow. It looks something a lot like my background that you can see behind me. My virtual background I chose today is what we call a star spectrum. This is what it would look like when you break up a star's light. It has a rainbow, but it has all of these like black lines in it. And all those black lines tell you something about the star. Think of it like a barcode, like a UPC code for your groceries. Each of those have a unique pattern, and when you scan them, they have a unique information. That's exactly what this is like in nature. It's really cool. So what you're seeing here, and this, again, as Kurt mentioned, this is college level classes. So it gets a little complicated, but it's really fascinating. When you have hydrogen gas and you excite that hydrogen gas, you add energy to it. It emits photons, which are light particles. So hydrogen gas will shine when it is energized. When it has energy, hydrogen gas will shine. This is how stars work. But hydrogen gas only emits on this dark blue line, this cyan line, and this red line. It only emits at those very specific colors, nothing else. So it does not show this continuous rainbow. It only shows the dark blue, the cyan, and the red. And that is the case for any hydrogen anywhere. So when you look at a light and you see that pattern, you know that it has hydrogen in it. Very valuable information. Same for helium. If you have helium gas and it is shining, it's excited and it's shining, emitting photons, shining light, it'll have these specific bands. Okay, and then it gets more complicated as you go down the periodic table. But when you put those all together, then you get something super complicated like the image behind me. And sort of a more simplified version would be this image below here. Now you might be thinking, why are there like bright lines up here, but there's black lines down here? Think of this bottom picture as a photo negative. So these black lines are the lines that a star is emitting light, if that makes sense. Okay, so it's a photo negative. And this is how we study starlight today. This is how we have discovered the expansion of the universe. This is how we classify all of the stars that we see in the sky, how we learn about nebulae. It's pervasive throughout all of astronomy. It really just opened the floodgates in terms of how we could understand the universe and what information we could gain by looking at it. And this is where the stellar classification system started. So I kind of give you a little bit of the science overview there. This is sort of the historical overview of why do we have these letters and they aren't even in alphabetical order. It starts in Harvard in the late 1800s to early 1900s. The stellar classification system that we use today, that OBY, GM, I'm missing the letters there, but OBAFGKM, those letters that we use today, they all got started, that system was started and devised by early women astronomers. So you can see in this photo, these are all women from the late 1800s. Now, that's easier to just say in 2021, okay, there are these women and they devised the stellar classification system. That's cool. They must have been smart. Moving on. No, this was truly incredible. This was a time when women going to college or working outside of the home was virtually unheard of. These women were not only working out of the home, but they were revolutionizing the field of astronomy. Contemporary science at the time, it actually warned against women in education and a belief that women were too frail to handle the stress of academia. In fact, there was a doctor and Harvard professor, so at the same college that these women were at the same time, this professor, Edward Clark, he wrote a book that stated, a woman's body could only handle a limited number of developmental tasks at one time. So girls who spent too much energy developing their minds during puberty would end up with underdeveloped and diseased reproductive systems. This is the world that these women were living in. And so the fact that they developed a stellar classification system that and then refined it into something that we still use today after 100 years is truly incredible. Really, really fascinating story. And it starts with these women here and this guy in the back, Pickering, oh my gosh, I forgot his first name. Yeah, it was Edward. That's why. Edward Pickering. He had a problem. Edward Pickering was the director of the Harvard Observatory, and he was doing something brand new. He was, it's actually the beginning of astrophotography. He was one of the first to take photographs through a telescope of the nighttime sky. He was taking these photo plates to capture this light, much in the way that I've described, where you saw the spectrum lines. Now they were in black and white, but they could relate them to color based on frequencies. They knew exactly where the lines were on the picture and how that corresponded with light colors. So anyway, he was taking tons of these, of thousands of stars, and didn't have the manpower to review them and classify them. So, and the people that he did have working for him, he was not happy with the quality of their work. So he hired his maid, Wilhelmina Fleming, he hired her at half the price he would have hired a man. She worked for 25 to 50 cents an hour. But Wilhelmina Fleming, and I'm assuming Pickering knew this, that she was had a real gift for math. She was a brilliant mathematician. She had been teaching other people maths since the age of 14. And she picked up this work and kind of ran with it. She was very successful. So he began hiring more women. Fleming was so adept at this, they call it computing, human computers at the time, because computers weren't invented yet. So she was so adept at computing and copying these star spectra and organizing them that she worked there for 34 years, and she ended up managing a lot of mostly women doing this work. So if you want to learn more about Wilhelmina Fleming, she was an incredible woman, has an incredible story. And Nishan wrote a whole script about her life, and it's in a video called Life of a Scientist on our YouTube channel, and I think it's on our Facebook here. That just came out last week. And he talks in way more detail about Wilhelmina than I am going to today. But she's a fascinating woman. So if you want to learn more about her, please see Nishan's video on our YouTube or Facebook channel. So during her career, Fleming, can't remember which one she is in this photo. I can point her out in a minute on a different photo. But she classified more than 10,000 stars. She discovered 59 gaseous nebulae, over 310 variable stars, stars that brightness changes, and she discovered over 10 novae, including the wildly popular Horsehead Nebula. Oops. This is in the constellation Orion. It's one of the most beautiful areas of the sky. Astrophotographers today love to take pictures of this. This looks like a little horse head. That's why we call that the Horsehead Nebula. And she discovered this. So these women categorized these photographic plates and created a classification system that went from the letter A all the way to the letter Q. Q was, the last letter there was like leftover things that they weren't quite sure where it belonged, or things that weren't stars. But they all, it looked at the hydrogen absorption line. So how bold that absorption line was for where hydrogen was supposed to be. If it was really, really thick and bold, it would be classified as an A star. If it was if it was really faint and you could barely see the hydrogen lines, then that would be A, B, C, D, E, F, G, H, I, J, K. A P star. And then Q are the ones that aren't stars or they weren't sure of. And so that was the standing stellar classification system for most of Fleming's era. In this photograph here, I love this photo because they're actively engaged. This is what they looked like when they were classifying these stars. This is Wilhelmina Fleming here, standing up. This is Annie Jump Cannon, which I'm going to talk about. She's she's responsible for the classification system as it stands today, and very, very important in this work. So was Henrietta Leavitt, who is in the back here. Her work is what led to us ultimately understanding the expansion of the universe. So her work, it was what kind of raised some red flags to go, wait a second, this doesn't look right. And then later we realized what she was seeing and observing was the effect was the expansion of the universe. So she's really, really important work, huge historical figures all in this photograph. Annie Jump Cannon over here, as they started to begin to understand what these lines really meant, because, I showed you, we already have the answers to the test, right? This is what hydrogen lines look like, and this is what helium lines look like, and this is what they look like all together, and that makes up the composition of a star and all that. They didn't have all the pieces of the puzzle at that time, but it was coming together. And so as they started to realize the relationship between the temperature of a star, and its size, and I guess the importance of the temperature of the star and how its composition. It's a little complicated, but a star's composition is greatly affected by its temperature. And that was something that they were starting to learn. And so Annie Jump Cannon started to think, why are we classifying these stars by their hydrogen absorption or emission lines when maybe we should be measuring them or organizing them based on their temperature. And you saw that pretty, when you do that suddenly, you have this pretty line, right? There's a lot of correlations there. And so what Annie Jump Cannon did, and a couple of other notable women in this Harvard Observatory, they reorganized the letters because these letters were so well established. They were published in all these astronomy papers. They were totally used. They were household names, I guess would be the way to say it, in the astronomy circles. They couldn't just rename stars, because then it'd be like, oh, this is a O star. You remember it used to be an A star, but now it's an O star. And then this star is an A star now, but it used to be an M star. That's confusing. So they simplified the system and reorganized it based on a star's temperature. And that's how you end up with an O over here, a B here, an A here, and so on. And the fact that we still use this system today, over 100 years later, is truly a testament to the important work that these women were doing. So I think that's what I have. Do we have any questions?
I do not see anything in the feed. Maybe people are just doing the if you say so thing right now, but that is a lot of information.
Yeah.
An interesting thing about this is astronomy is this juxtaposition of cutting edge stuff that we know, all this quantum mechanics, and these historic things like this rather cumbersome classification system we're using from over 120 years ago, which is a fascinating thing.
I love that. I mean, astronomy sits between science and art and history, and but there's so much history in astronomy, and then also, like you said, we're pushing the bounds of our knowledge. So it's an interesting mix, and I think that this story really highlights that. But it is a lot, so it's kind of an information dump this weekend. But we are coming back in 2 weeks for another Keep Looking Up, and good or bad, you can see it either way. It'll be our last one for a while. So our last
maybe ever, because we are planning on going back live. It may be our last Keep Looking Up ever.
Yeah, so that's why it might be our last Keep Looking Up, because we hope to be reopening the planetarium in the fall. We normally, our normal new season would start in September. So that's where we hope to just kind of reopen with a new season in September. Fingers crossed that we all get to that point. That will be really happy and great and wonderful. So what that means is, though, that we're going to be wrapping up for the summer with our online programming. But our next Keep Looking Up is going to be a whole lot of fun. So please join us. I'm really excited about it. It's going to be all star lore. So we'll be bringing you star stories. It's just going to be us and you and the stars, and we're going to tell you stories about the stars from different cultures.
But not just the Greeks.
Yeah.
We use the Greek constellations. We've been showing you the Greek constellations, but they were not the only people that had stories about the sky.
Nope. No, there were many other, basically every culture, almost every culture across time, across this planet, have looked up at the same stars, like Eleni was saying, and they have different sometimes similar, sometimes very different stories. And I don't know them all. I don't even know a fraction of them, but I'm excited to share with you what I do know. So if you have any Star stories to share, you can bring them with you, or questions or anything, and it'll be a really good time.
Now, before we go, Eleni, you need to get back on screen here. Yes, this is Eleni's last time with us on Keep Looking Up, as we said. So congratulations once again. She started working with us during the Great Eclipse in 2017, before she was even a freshman. And here we are sending her off. So thank you, Eleni, for everything you've done for us.
Oh, thank you guys. Thank you for having me. This is the best job ever.
All right, I think we are going to wrap up here tonight. Thank you for joining us, and remember to keep looking up.